For decades, scientists knew that Earth was losing enormous amounts of heat through the Arctic and Antarctica. But there was a problem. Much of that heat was escaping in wavelengths that satellites were barely measuring. Now NASA has spent 2 full years watching this invisible energy leave the planet. 2 satellites small enough to resemble shoeboxes have repeatedly crossed the Arctic and Antarctic, measuring heat that human eyes cannot see. The mission, called PREFIRE, has now captured 2 complete seasonal cycles at both poles, revealing how dramatically polar temperatures rise and fall through the year. More importantly, the satellites are measuring a part of Earth's energy system that had never been comprehensively observed from space. And that missing energy matters far beyond the ice. To understand why, imagine Earth as a machine that is constantly receiving and losing energy. Sunlight enters the system. Some is reflected by clouds, snow, and ice. The rest is absorbed by the land, oceans, and atmosphere. That absorbed energy eventually has to go somewhere. Earth releases it back towards space as infrared radiation. If the planet absorbs more energy than it emits, temperatures rise. If it loses more than it receives, temperatures fall. The difference between those 2 flows is Earth's energy budget. But the planet does not receive solar energy evenly. The tropics absorb much more sunlight than the polar regions. Atmospheric circulation and ocean currents then transport some of that excess tropical heat toward the Arctic and Antarctica. The poles act partly like giant exhaust zones. Heat transported away from the tropics eventually reaches high latitudes, where the surface and atmosphere radiate energy into space. That loss helps regulate the temperature of the entire planet. Scientists have understood this broad mechanism for decades. What they lacked was a detailed measurement of one crucial part of the radiation leaving the poles. It is called far-infrared radiation. Infrared light sits beyond the red edge of human vision. We cannot see it, but we experience some infrared radiation as heat. The far-infrared portion occurs at even longer wavelengths. It is especially important in extremely cold, dry environments like the Arctic and Antarctica. NASA says nearly 60% of the energy Earth loses to space occurs in the far-infrared. Yet before PREFIRE, this part of the spectrum had never been comprehensively measured on a global scale. In regions such as the Arctic, large portions of the outgoing energy spectrum were effectively missing from systematic satellite observations. That is an extraordinary blind spot. Imagine trying to understand how quickly a house loses heat during winter while your thermometer ignores more than half of the radiation escaping through the walls. You could still estimate what was happening, but your calculations would depend heavily on assumptions. Climate models faced a similar problem in the polar regions. They had to estimate how snow, clouds, ice, water vapor, and the surface interact with far-infrared radiation without the comprehensive measurements needed to test those estimates directly. PREFIRE was built to fill that gap. The mission consists of 2 nearly identical CubeSats launched from New Zealand in May and June 2024. Each carries a thermal infrared spectrometer developed by NASA's Jet Propulsion Laboratory. These instruments separate outgoing heat into different wavelengths, allowing researchers to see which parts of the polar environment are releasing or trapping energy. Their far-infrared measurements have roughly 10 times finer wavelength resolution than previous comparable sensors. The use of 2 satellites is particularly important. They travel in asynchronous near-polar orbits, meaning they cross similar regions at different times. Instead of observing the same location only once each day, PREFIRE can obtain snapshots separated by hours. That helps scientists detect changes that happen quickly. A cloud system can move across the Arctic. Sea ice can fracture. Snow conditions can change. A warm air mass can arrive. The 2 satellites give researchers a better chance of seeing how those events immediately alter the amount of heat leaving Earth. The first 2 years of observations reveal the enormous seasonal contrast between the poles. During Arctic winter, months of darkness allow temperatures to plunge. When sunlight returns, the surface warms and vast regions of tundra, snow, and sea ice begin thawing. Antarctica behaves differently. Even in summer, much of the continent remains below freezing. Then the return of winter produces some of the coldest temperatures anywhere on Earth. NASA's new visualization turns those seasonal changes into pulses of color spreading across the poles. But temperature is only the visible part of the story. Every change in temperature alters radiation. Every change in snow or ice changes how the surface interacts with incoming and outgoing energy. And every cloud moving above that surface can either trap heat below or modify how energy escapes into space. This is where PREFIRE becomes especially valuable. Clouds are one of the most complicated elements of the climate system. They can reflect sunlight and cool the surface, but they can also absorb infrared radiation and prevent heat from escaping. Water vapor also absorbs infrared energy. In the polar atmosphere, where both temperature and moisture can change dramatically, small differences in how models represent clouds or water vapor can alter estimates of the energy budget. PREFIRE directly measures the wavelengths most sensitive to many of these processes. The satellites have already revealed that different forms of ice can emit different amounts of far-infrared energy. NASA reported that, at PREFIRE's longer wavelengths, radiation escaping from one type of ice can differ from another by as much as 5%. Similar observations using shorter infrared wavelengths do not reveal the same distinction. That means an ice-covered region cannot always be treated as one uniform surface. Fresh snow, old snow, sea ice, glacier ice, and ice containing different structures may each interact with heat differently. A 5% difference may sound small. Across millions of square kilometers of polar terrain and over months of continuous darkness, those differences can become significant components of the energy budget. And that may help researchers understand one of the largest mysteries in modern climate science. Why is the Arctic warming so much faster than the planet as a whole? NASA notes that the Arctic has warmed more than 2.5 times faster than the global average. Several processes contribute to this amplification. As reflective snow and sea ice disappear, darker land and ocean absorb more sunlight. Warmer air holds more water vapor, increasing the greenhouse effect. Clouds change. Ocean heat enters the Arctic. Atmospheric circulation transports additional warmth northward. But all of these processes ultimately involve energy entering, moving through, and leaving the system. Without accurately measuring the outgoing energy, scientists are effectively trying to understand the acceleration while missing part of the exhaust. PREFIRE provides measurements that can test whether models are representing this energy loss correctly. The consequences extend far beyond polar temperatures. The amount of heat retained in the Arctic influences sea ice. Sea ice influences ocean circulation and how much sunlight the surface absorbs. Polar temperature differences help shape atmospheric circulation. Ice sheets influence sea level. Snow accumulation affects freshwater storage. Cloud and moisture patterns influence storms and precipitation. NASA scientists say the energy movement observed by PREFIRE affects systems ranging from ice sheet stability and river flows to weather and shipping conditions. The mission could therefore improve weather prediction as well as long-term climate projections. PREFIRE was originally designed around the poles, but NASA has extended the mission through at least September 2026 and expanded its scientific focus to the entire planet. The satellites have actually been collecting data outside the polar regions during their orbits all along. Researchers can now examine how far-infrared radiation behaves in tropical clouds, humid atmospheres, deserts, and other environments. One target will be the size of ice particles inside clouds. These particles influence how radiation moves between Earth and space, and improving their representation could help weather models better simulate storms and precipitation. 2 satellites roughly the size of shoeboxes are therefore studying a process operating across the entire planet. But their most important contribution may remain at the poles. For years, scientists could watch sea ice disappear with visible and microwave satellites. They could measure ice sheet elevation. They could track atmospheric temperature and ocean currents. Yet part of the energy responsible for all those changes remained largely invisible. PREFIRE is finally measuring it directly. The mission does not reveal a newly discovered source of heat hiding beneath Antarctica or a mysterious energy escaping from the Arctic. The discovery is more fundamental. Scientists are obtaining a clearer measurement of a process that has always been happening but had never been observed in enough spectral detail. Earth absorbs enormous quantities of energy near the equator. The atmosphere and ocean move part of it toward the poles. Snow, ice, clouds, water vapor, and the surface determine how efficiently that energy finally escapes into space. For 2 years, NASA's smallest climate satellites have been watching that planetary exhaust system breathe with the seasons. Winter arrives and the poles plunge into darkness. Summer returns and temperatures rise. Clouds move. Ice changes. Heat escapes. And every one of those invisible photons carries information about whether Earth is gaining energy, losing energy, or moving toward a different climate. For the first time, scientists can watch much more of that hidden energy leave the planet.